Hey everyone, we're getting set to start with optimization, which is section 5.4 in your calculus book. And optimization is one of those really big, important strands here in calculus. It's one of the really big applications for the derivative things we've been doing. So let's take a look at optimization and modeling. Next window. So we've got at some point after the zombie apocalypse, we're going to need to start growing food. For this exercise, we're going to build a compost bin for our zombie garden on a patch of land constrained by a parabola. Our zombie compost bin is going to be 3 feet tall, and we're going to optimize the volume of the bin based on the available parabola-shaped patch of land. So, not that crazy as far as calculus goes. What the heck does we mean by optimization? Well, in most cases, we're going to say, well, what is the quantity that we're interested in? And then we're going to use mathematical techniques to either find a maximum or a minimum for that function that is interesting to us. So in this case, we're looking at the volume of our compost bin. We want to make the compost bin probably as big as possible, given that we have to put it on this parabola-shaped patch of land. So mathematical models are sets of equations that behave in ways similar to the physical phenomenon. So as an example, you already know the relationship between the sides of a right triangle. There's a little rundown on the Pythagorean theorem. And that equation, a squared plus b squared plus c squared, is going to be a mathematical model that you can use for any right triangle if you're interested in the sides of that right triangle. Another one that we can look at is this constant acceleration from physics. I think most of us know that position is equal to 1/2 of at squared plus v initial t plus initial position. And a is acceleration, v naught is initial velocity, and s naught is initial position. And if we're talking about free fall on Earth, we're going to use a as negative 32 feet per second, or negative 9.8 meters per second. And yes, I like to write out meters per second because I feel like it's more exact to the situation, more exact than meters per second squared. So let's take a look at that. One more thing here. Another powerful technique used in mathematical modeling would be to overlay a coordinate axis on those physical objects and then assigning those important locations with an x and y coordinate. So this is kind of why we learn the how to graph things, is because we're going to use those graphs as our mathematical models. So here we go. We've got you probably have this chart in front of you. I just went and filled it all out. You're going to need to know the area and perimeter of certain objects. For example, if you have a rectangle, area is length times width, perimeter is 2 length plus 2 width. If you have a parallelogram, the area is the base times the height, and that's the perpendicular height. One that we use a lot in calculus is this area of a trapezoid, 1/2 b1 plus b2 multiplied by the height. So I'll just pause it here, and you can notate these if you already know these. Pause it now and copy those down. Okay, these are for 2-dimensional shapes. And then these right here are for 3-dimensional shapes. So we'll go through some of the hits here. You've got a cylinder, pi r squared times the depth, and the surface area, should you need it, 2 pi r squared plus 2 pi r depth. And then let's see, a cone, that's a good one. 1/3 pi r squared times the depth or the height of the cone. And then the surface area is pi r squared. The pi r squared part is the area of the base, plus pi r multiplied by the slant height. Yeah, you're not getting away from the slant height just yet. So go ahead and pause it here and copy these down. And let's take a look at our next section here, which is a 6-part plan for optimization. Really, I think of it as kind of like a 5-part plan, because if we take a look at the first part, it's just understand the problem. Okay, you got to know what the problem is asking for. If you have a misunderstanding with what the problem is asking for, you're kind of guaranteed to get that problem wrong. Next, you're going to develop that mathematical problem. You're going to draw pictures of the physical phenomenon. You're going to introduce variables to represent the quantity whose extreme values gives the information sought. We're going to call that the primary equation. And we're going to reduce that primary equation to a single variable. Now that's kind of important for us, because right now we have calculus of a single variable. So we have to make sure that we can turn that equation into an equation of just one variable. For example, if the volume is equal to length times width times depth, the volume is an equation with 3 variables in it, and I've got to make that an equation with only one variable. So there has to be some substitution we're going to do. Number 3, you want to graph that function when possible. You want to find the domain of the function for that one variable. And you're going to determine what values of the variable make sense. Once you're done with that, we get moving on to the real calculus part here, which would be identify critical points and endpoints. You're going to solve the mathematical problem using the candidate test. That's why we learned that a couple of lessons ago. And finally, we're going to interpret that solution, translate that mathematical result into the problem setting, and then we're going to decide what results make sense. So let's get to the zombie compost bin. Here's the idea. The rectangular compost bin is built on a patch of land modeled by a parabolic equation y equals 5 minus 1/2 squared in the above x-axis, where x is given in feet. If the height of the bin is 3 and one side of the bin has to be on the x-axis, what dimensions will yield a zombie compost bin with the maximum volume? So first of all, we're going to understand the problem. We're going to write any notes below. Do we have any notes to write down here? I don't think I have any. We know it's going to be a rectangular prism. So that means that the volume is going to be length times width times depth. So that's a good thing for us to think about. Part 2. Develop a mathematical model of the problem and draw the compost bin on the graph of y equals 5 minus 1/2 x squared. So here is the graph of y equals 5 minus 1/2 x squared. And one side of my bin has to be here along the x-axis. The other sides, we're going to make this side here, we're going to make that as tall as possible. And that gives me a rectangular base for my prism. Now, if you want to know what that rectangular prism of a compost bin is going to look like, it's going to kind of look like this. But I think that kind of complicates the diagram a little bit much, so let's get rid of that. And let's talk about the bottom dimension of this bin. We have this part right here is the length of that, and that is 2x. Now it's 2x because we're going from, let's see, this length right here, that's going to be the same as the x-coordinate right here. But that's only half of the compost bin. We've also got this side over here. So this is x plus x, and that's 2x. The width of this compost bin is going to be the y-coordinate up over here. So what is the y-coordinate up there? And then the height or the depth of this compost bin, well, we're told that that's going to be 3 from the problem. So that's going to help us figure out the equation here. So the problem asks to maximize the volume. So it makes sense to make the volume formula our primary equation. Your primary equation is the thing that you want to minimize or maximize. So the shape of the bin is a rectangular prism. What is the formula for the volume of a rectangular prism? Of course, it's just length times width multiplied by depth. Are there any quantities in the volume formula that are constant? Actually, we know that the depth is constant. This is always a good thing to ask pretty quickly. As soon as you get your basic primary equation, you want to ask yourself if there's any constants in that equation. And then you want to rewrite your primary equation, substitute all those constants in. Constants, though, if it's a variable, you got to keep it as a variable. So the depth is always going to be 3. So actually the volume formula is just 3 times the length times the width. Now we already spoke about the length and the width, how the length is 2x and the width is just the y-coordinate. But we didn't say what the y-coordinate is. The y-coordinate, and this is pretty typical, the y-coordinate is just the equation of the parabola. Because up over here, since we're on the parabola, we know that y is equal to 5 minus 1/2 x squared. So that actually makes sense. If the length is 2x, the width is 5 minus 1/2 x squared. That means we can use the substitution for length, width, and depth to rewrite our entire equation using the single variable x. We know the volume is going to be 3 times 2x times y, which is 6xy. And we know that y is 5 minus 1/2 x squared. So when we simplify that, we get that the volume is equal to 30x minus 3x cubed. And that's key for us. We have to make sure that our volume formula, our primary formula, has only one variable in it, x in this case. So let's see what we do next. The next thing we want to do is we want to graph the function. For what values of x does the mathematical model make sense? Okay. So let's see this. A few thoughts. Although the x-coordinate can never actually be equal to 0 or 3, remember x is the same thing as the half of the width, and if half of the width is 0, the entire width of the compost bin is also going to be 0. What does that mean if your compost bin has a width of 0? Not much. If the compost bin has a width of, or half the width is 3, that means the entire width is 6. Well, what's wrong with 6? Well, if the entire width is 6, let's go back to our equation here. If this entire width is 6, what's the length of this going to be? It has to be the parabola, and the parabola meets the x-axis at 3 and negative 3 when the length is 6. So that would mean that we have a parabola with 6 in length and 0 in width. And what the heck does that mean? So we can't actually get to 0 and 3. But we're going to pretend that we can because this is a theoretical model. And even though it doesn't physically make sense, it does make sense in this mathematical model sense. So we're going to pretend that we can actually make a compost bin with either a length of 0 or a width of 3. Sorry, a width of 0 or a width of 3. So this right here, this is my graph of my of the volume formula. And the first thing that I want to tell you is right here, you don't even have to do a whole lot of math. I mean, we've already done a lot of math, but right at the top of that parabola, or this parabolic shape, it's not actually a parabola. That's the maximum volume right there. We already know the answer without doing any calculus, just by graphing our volume function. That doesn't excuse you from doing the calculus, because this is still a calculus class, but you should, take a look at that. You know already what the maximum volume is going to be. Okay, so 0 f of 0, where is that? That is right here. Why is that point significant? Well, that's going to be the smallest dimension that we can do in the x direction. So x has to be 0 or bigger. How about square root of 10, f of square root of 10? Where do you suppose that is? Well, that's somewhere a little bit north of 3, I think. So square root of 10, f of square root of 10, that is right here. Why is that point significant? Well, that's the smallest dimension in the y direction. So if we take a look at this graph over here, I know I said 3 before. It's not actually 3. Oh, over here, I'm sorry. I know I said 3 before. It's not actually 3. This graph, y is equal to 0. If we solve that, we get that 5 minus 1/2 x squared is equal to 0. And guess what that turns into? That gives me x squared is equal to 10. And when you solve that, you get x equals 3.16227. So this is actually a good thing for you to realize if you're dealing with these and you're trying to figure out your domain. A good thing for you to do is probably to set each of the variables, each of the dimensions equal to 0, and that will give you the maximum and minimum dimensions in most cases. So square root of 10 and f of square root of 10, well, that is the smallest dimension in the y direction. So we talked about this already. What was the maximum value of f of x? And we saw from the graph that that maximum value of f of x, it's about 36 cubic units. So that takes care of number 3, kind of analyzing this graph of f. And in this case, f is the volume of the compost bin. So we're going to get into the more calculus-y stuff now. So identify the critical points and endpoints. As customary in calculus, we just decided to relabel the function from volume to f of x. At this and all intermediary calculations, you should not round your results. So what is the minimum value of x? We already talked about that. That's just 0. The maximum value of x, that's the square root of 10. That means that x must be between 0 and the square root of 10. Okay. A, B, and C down over here. First of all, what is f of x? Well, that's the volume formula, and we already solved the volume formula up over here. The volume formula is 30x squared minus 3x cubed. Next, what part B in this number 4? For B, what is the equation of the derivative? That's just 30 minus 9x squared. Part C, solve. Set the derivative equal to 0. That means 30 minus 9x equals 0. Factoring out a 9, that means that 30 over 9 minus x squared is equal to 0. Doing even more math, that means that 9 multiplied by root 10 over 3 minus x, root 10 over 3 plus x is equal to 0. That's a very mathematical way of doing things, which means that f prime of x equals 0 when x is 10 root 3 or negative 10 root 3. But of course, negative 10 root 3 is not in the domain. Remember, x has to be between 0 and root 10, so it has to be positive. Okay, now that we have this, remember that this is a critical value. So we're going to use that in our candidate test. Let's take a look at our candidate test in number 5. Solve the mathematical model, which in these cases, that just means the candidate test. So what are the candidates that we need? We need 0, square root of 10, and square root of 10 over 3. Okay, how about at 10, at square root of 10, what is f of the square root of 10? Well, f is equal to 30 minus 3x squared. And when you substitute square root of 10 in there, you get 0. And when you substitute square root of 10 over 3 into the volume formula, remember the volume formula is this one right here. What do you get? What is f of square root of 10 over 3? Well, it's 36.51483, which we already knew. Okay, so we are ready to do our analysis. Clearly, our maximum value is 36.51483, and the zeros are both minimums. Because there's the same value, there can be more than one minimum. There can be more than one maximum as long as it's the same value of the function. So we've done it. We have found the maximum volume, and we've also found out what it takes to get the maximum volume. So we're going to interpret the solution, always write a few sentences. So when x equals root 10 over 3 and y equals 10/3, the compost bin has a maximum volume of 36.51483 when the dimensions of the bin are 3 by 3.651848 and 3.3333. So that takes care of it. Those are the 6 steps, which we will also put here in the important ideas. Understand the problem, develop a mathematical model, use those constraining equations, and then you're going to take that mathematical model and try to bring it down to one variable, graph the function and find the domain of the function, identify critical points and endpoints, solve the mathematical model with a candidate test, and then interpret the solution. So take a second if you need to pause this and write this down. And let's move to check your understanding. Okay, your zombie garden is built on the side of a river so that it only needs to be fenced in on 3 sides. Take a look at the diagram. You have enough material to make 500 feet of fence. So what dimensions should you make the zombie garden to maximize the area of the garden? So we've already kind of started you on this with this diagram. This side is going to have length x. This side here is going to be length x. This side over here is going to be length y. We know that x plus y should equal 500 because we only have 500 feet of fencing material. And we also know the area of this garden is x times y because we're pretending that this is going to be a rectangle. So let's get that mathematical model going. We want to maximize x times y, so that's our primary equation. We're using p for perimeter, even though it's not truly the perimeter, but the amount of fence we need to use is 500, and that's going to be x plus y plus x. Let me just highlight that for you. X times y times x. Altogether, that is 2x plus y. That's got to be 500. And we want to keep one of the variables, so we're just going to solve for y. We're going to say that y equals 500 minus 2x. And where is that 500 minus 2x going to go, do you think? Finally, we're going to relabel the area as f, our function. We're going to say f is equal to x times 500 minus 2x, which is just 500 minus 2x squared. Let me zoom in a little bit here for you. Oh, a little bit too much. There we go. All right, next we're going to graph the function and find the domain. Let's go ahead and graph that. I'm going to grab my calculator. There we go. With x is 500 minus 2x squared. Let's try to make a window here. Well, what do you think the smallest that x could be? The smallest that this fence could be in the x direction. And it doesn't have to make sense, but you know that that x direction, the smallest that it could possibly be, would be 0. Let's go to our window and we'll set our x minimum to 0. Oh, it's still 0. So that's good. What's the biggest that x could be? Well, the biggest that x could be was if y is equal to 0. And if you look over here, if y is equal to 0, that means x needs to be 250. Remember what I said earlier. Take the two variables in this case, make each one of them equal to 0, and that'll help you find the maximum and minimum of, in this case, x. So 250 should be our x maximum. Okay, do I know what the maximum area of this is? Well, let's see. If the area is somewhere, if x is somewhere in here, let's say 100. So let's pretend that we make a square here, 100 by 100. And I'm picking 100 because it's the half of 250. If it's 100 by 100 approximately, that means that my height should be about 10,000. So let's see if that helps us find our graph. So push graph now. Let's see what that looks like. Ooh. Oh, down the other side. So apparently I need to make this graph taller. This is often something that's going to happen. I don't think I'm even close with 10,000. Let's make this, let's multiply this by 5. 50,000. Let's see, is that going to give me the entire graph? Ooh, yeah, this is going to be good. There we go. So here's our graph of the function. We know where the maximum here, where the maximum is. The maximum area is going to be somewhere over here, right around 125, I think. Over here is our 0 to 250. And yeah, this makes sense. The maximum area should be right over here because this is our area graph. So we've graphed the function. We know something about this for the domain. What is the domain? X should be between 0 and 250. Now remember that I'm making these inclusive of 0 and 250 because theoretically it's possible, but practically it's not possible. Okay. Identify critical points and endpoints. Endpoints, we got that. That's 0 and 250. But what about the critical points? Let's take our derivative. F prime is equal to 500 minus 4x. We want to set that equal to 0. That's a really easy equation to solve. That's just 500 on 4, which, if I'm not mistaken, that's just 125. So we only get one critical point. It's 125. So now we're going to use our candidate test. Here's our chart, and when x equals 0, f of x is equal to 0. That's our minimum. When x equals 250, f of x is equal to 0. That's our maximum. And when x equals 125, we get 31,250, and that's our x. So now's a good time for us to take out our calculator. Let me show you a really quick way of doing this. If our y equal function is over here, this is our primary equation. If I go to, well, first I have to set my table because we're going to make a table. And this is the way you want it. Independent, ask, dependent, auto. Go to second graph for the table, and it will ask you all the coordinates that you want. So we can just put a 250 here, and that'll give me that. Actually, we should have done 125, and then 250, and that gives us our table. Try and get these both in the same view. That's the same thing. That's a really good way to do your candidate test. Go ahead and use the table function. Again, table set, second window, ask, auto, table, second graph, and then just fill in your x coordinates. All right, that's our window. We know where our maximum is, so we can interpret our solution. The maximum area occurs when the dimensions are 125 by 250. How did I get that 125 and 250? 125 is pretty easy. We knew 125 because it was our critical point, and of course that's our value of x. The 250 comes from the value of y, and you'll get that by substituting over here. 2 times 125 is 250. 500 minus 250 is 250. So that's where we got our y dimension. The maximum area is 31,250 square feet. I am partial to you writing out square feet and not putting a feet to the second power. Save that for the physics guys. So that is our calculus trainer for today. Hope that all makes sense to you, and I hope those 6 steps really will give you a framework for solving all of your optimization problems. See you next time, and have a good one.